this is a recap of what we did in the last class on Thursday. For those of you who couldn't make it in the morning class, we were looking at the case of constant wall temperature boundary condition, and when you apply earlier when we did the case of constant wall flux, okay, so there we came to the conclusion that your dTm by dx is equal to dt wall by dx, and these two terms got cancelled and your dt by dx is equal to dt wall by dx. So all the three can be equal only if they are equal to a constant, and therefore the variation of the temperature at any radial location as well as your wall temperature and mean temperature, they have to be parallel to each other and they have to be a linear line. Okay. When it comes to the case of constant wall temperature, so this comes to the fact that dt wall by dx is a constant, and therefore these two terms will get nullified. So you have dt by dx equal to T minus T wall by Tm minus T wall into dTm by dx. So therefore your dt by dx is now related to your dTm by dx. Now coming to the energy equation, so we will substitute this whatever conclusion that we made. So we will, instead of dt by dx, we write that in terms of T minus T wall by T mean minus T wall into dTm by dx. Okay. Also, since we have already calculated the velocity profile, which is a parabolic profile, we have substituted the parabolic profile into this expression. Now what is the problem with this? Unlike the case of constant wall flux boundary condition, there your dTm by dx was a constant. So therefore, so this side, this was not there, you had only dTm by dx. This side it was t as a function of r, so you could directly integrate this. This was integrable straight away, and you can find the temperature profile with respect to r and apply the boundary condition. Okay, so that was a very straightforward way. Now if you look at it, this dTm by dx is not a constant. Okay, so this is now changing, and we don't know how exactly it is changing. Strictly speaking, we last time derived how the profile should vary. If you plot your profile as a function of x, the wall temperature is a constant, however your mean temperature will vary such that the difference between the mean temperature and wall temperature is exponentially decaying function. So at x going to infinity, the difference goes to 0, correct. So therefore this is the way that the mean temperature varies. Okay, so having known this, you have again on the right hand side t, which is a function of both x and r. So you look at this equation now, it is a partial differential equation, and there is a chance that you can convert this into an ODE, provided you can express your dTm by dx as a function of dt by dr. Okay, so then you can also substitute for T minus T wall by Tm minus T wall in terms of theta, and now since d theta by dx is 0, so theta is only a function of r. So then you can convert this PDE into a nice ODE. So this is how we are doing it. So from energy balance, my dTm by dr can be related in terms of the wall heat flux as dt by dr at r equal to 0, and when I substitute that into the earlier energy equation, so now I have an equation where I can use phi to denote T minus T wall by Tm minus T wall. Okay, so therefore I can non-dimensionalize my radial coordinate also. I can introduce a non-dimensional radial coordinate which is r by r naught, which is r naught is the radius of the duct. So final resulting expression, if I substitute that, will come out in the form that is presented here. This is nothing but an ODE which can be solved by shooting method, once again iteratively. So you look at the boundary conditions, so phi at r star equal to 1, that is corresponding to r equal to r naught, so that should be 0 because there your T will be T wall, and at r star equal to 0 you should make use of the fact that the profile is symmetric and therefore the slope has to be 0. So these are the two boundary conditions. This is a second order ordinary differential equation. So we can solve the ODE with the two boundary conditions. So how do we do this once again we can make use of the shooting technique to get to solve this equation and also to get the value of Nusselt number. Okay, I will just briefly explain how you will be doing this. It is very similar to the earlier shooting technique problems. Only thing, see now the coordinate system, what you have been working with starts with the center. So what I would like to do is, when you solve this with shooting technique, you can start working from the coordinate system which starts from the wall. Okay, so why we can do that is that at the wall you do not know the gradient. Okay, also you do not, the gradient is related directly to your Nusselt number. So in this equation you do not know what is the Nusselt number, also you do not know what is the gradient at r star equal to 1, correct. So both are not known. So in order to simplify this problem, if we start working directly with a coordinate system starting from the wall and marching to the center, you can directly guess the value of nu, and therefore that will give you a guess for directly the slope at the wall, right. So you understood the problem. So right now if you are marching from the center, okay, you need a boundary condition for phi at r star equal to 0. So you need to guess a value of phi at r star equal to 0, and again you need to guess the value of Nusselt number, both are unknowns. That will involve two guesses and that will become a little tedious, whereas if you start from a coordinate system from the wall and proceed to the center, you should need a guess for the slope at the wall, and that is directly related to your Nusselt number. So both in one shot you get it. Okay, so therefore I am going to shift the coordinate system from the center to the wall. Okay, so I will have a coordinate system. Right now I have an r star non-dimensional coordinate system ranging from 0 to 1. I will shift that to r prime. How do I shift it? 1 minus r star, so that when r star is equal to 0, r prime equal to 1, when r star equal to 1, r prime will be 0. So then I can substitute that into, let me call this as equation number 1, substitute into equation number 1, and I can rewrite in terms of r prime. Okay, that will come as 1 minus r prime d by dr, 1 minus r prime d phi by dr prime. Of course your dr prime will be minus dr star, right. So that should be equal to minus twice Nusselt number into phi into 1 minus 1 minus r prime the whole square. Instead of r star square I have 1 minus r prime the whole square. So this is how my ODE will be, and the boundary conditions will be phi at r prime equal to 0 will be what? So now I should also make the boundary condition transform to r prime instead of r star. This should be 0, and d phi by dr prime at r prime equal to 1 should be 0. Okay, so now I can, here your Nusselt number is defined as twice d phi by dr prime at r prime equal to 0. This is how your Nusselt number is defined, correct. So earlier it was defined as, in this case your Nusselt number was defined as minus twice d phi by dr star at r star equal to 1. Now when you substitute for dr star as minus dr prime, so that will become, Nusselt number will be twice d phi by dr prime at r prime equal to 0. So that is starting from the top, from the wall and towards the center. So now this equation is easy to be solved by the shooting method. So we will call this as 2. So So by shooting method, first I should reduce, before for applying shooting technique I should reduce the second order ODE into two first order ODEs. So by introducing the fact that my d phi by dr prime is equal to psi, this is one of the ODEs. Therefore if you substitute into equation number 2, you should be getting d by dr, this is all your dr prime into 1 minus r prime into psi should be equal to minus nu phi into 1 minus r prime into 1 minus r prime the whole square. Okay. So this is equation number 3, this is equation number 4. So now you have reduced equation 2 to 2 first order ODEs, one you have to solve for phi, the other you have to solve for psi. So the boundary condition for this, so phi at r prime equal to 0, so that basically is 0. So that is sufficient for solving this. Now for solving this you need psi, which is nothing but psi at r prime equal to 0, which is d phi by dr prime at r prime equal to 0. This is not known, this is nothing but what, Nusselt by 2. Therefore now you see you do not know the Nusselt number anyway, so you can guess a value of Nusselt number, and that is the guess for psi at r prime equal to 0. But what you know is basically psi at r prime equal to 1. Okay. So now this becomes an iterative process again. So you guess a value of Nusselt number, therefore you guess a value for psi at r prime equal to 0, you keep marching by the shooting technique, you shoot and you march, and you should make sure that your psi at r prime equal to 0 is equal to 0, so that satisfies the other boundary condition. So you have to do this iteratively, you keep guessing the value of Nusselt number, you change the value of Nusselt number until you satisfy this condition. So finally you end up directly getting the correct Nusselt number, that is it. Okay. So once again I will just write down the procedure. So solve 3 and 4 by shooting. So step 1 is to guess nu, and therefore hence your psi at r prime equal to 0 is calculated as nu by 2. That is the first step. Number 2, you solve 3 and 4 by say Euler method. Okay. So you can take a large value of, so you start from r prime equal to 0 up to r prime equal to 1. Okay. So unlike your external flows where your eta was going till say 10 or 15, now your range is defined. So your r prime equal to 0 to 1, and then check if whatever from your solution, if your psi at r prime equal to 1 is equal to 0. If that is true, then whatever you guessed is correct, that directly gives your nu. If not, you have to iterate till step 3 is satisfied. Now again for iteration we make use of an intelligent guess using the Newton-Raphson method. So here the Newton-Raphson algorithm will be psi. You need to basically guess the value of psi at r prime equal to 0. So therefore psi at r prime equal to 0 at k plus 2. So you first guess once, you guess twice, and then for the third guess you use the Newton-Raphson method, because again it needs at least 2 guesses to calculate the difference. So this will be equal to psi at r prime equal to 0, so k plus 1th guess plus, so this will be f of x divided by f prime of x. Now f of x is the condition that psi at r prime equal to 0 should be equal to 0. So anyway that, so this minus 0 should be 0, or this is equal to 0, right? Oh, r prime, oh sorry, r prime equal to 1. So in this case this comes out as 0, therefore this term should be I think this entire term then should come out as 0 here, because your f of x should be anyway 0, right? Your f of x is anyway 0, so psi at r star equal to 1 should be equal to 0. So therefore, so this numerator completely, so I think using the Newton's method here may not be that beneficial, because anyway, so this doesn't, this term is absent here, right? Is that right? Because you have your psi at r star equal to 1, this is your function which it has to be satisfied, this is equal to 0, your f of x is basically 0, okay. So therefore you have to guess your Nusselt number, so you can guess it iteratively, okay, trial and error.
Upon divided by the initial difference in guesses.
Yeah, okay, but this is actually the function that it has to satisfy, right? So the function it has to satisfy is f of x is equal to 0. So this is basically on the right, this is plus f of x by f prime of x. So this we are writing as a difference, but your f of x itself is 0 here, okay. So if you had a condition that this is equal to 1, then you can use it. This minus 1 equal to 0 is your f of x, they are similar to the external boundary layer, correct. So here we have directly your f of x is 0, so there is no point in using this particular method, will not give you, lead you anywhere. Huh?
Its solution it will be 0, so we can use it up to the solution.
Yeah, but this is what you have to satisfy, so you have to say that your f of when you say that this is the equation it has to satisfy, this has to anyway, we have to force it as 0 here, right?
Come to that step, like the difference is like suppose 0.2 and then we reduce it to 0.01.
You can just try and check, but I myself am thinking whether if this will work out for this kind of a problem with this boundary condition, because see, when you had the condition clearly that, say for example psi equal to 1, so you make sure that it has to satisfy psi minus 1 equal to 0, so that is a function there which it has to satisfy, whereas here psi is equal to 0 directly, okay. So anyway you can try your whether you can apply your Newton's method and see, but in my opinion this may not lead to the correct solution using this, so you can just do a wild guess. Anyway I will give you the solution, you can start with some guess close to the solution and you will find that your Nusselt number for this case comes out to be 3.658. So it is a constant value. Once again, as I said, if you have a fully developed thermally and hydrodynamically fully developed case, that is in region 3, you have a constant value, whether it is isothermal or isoflux case. For isoflux case, what do you remember the value? 4.36. So for the isothermal case, if you do a trial and error, you will finally see that at Nusselt number 3.658 this exactly satisfies this boundary condition. Psi at r star at r prime equal to 1 will be 0. Okay. So therefore, if you compare this to the isoflux case, you see the isoflux case has a higher Nusselt number. Okay. So there has been no concrete reason why people observe this experimentally also that this is higher, but some kind of an explanation can be given from the thermal boundary layer. Now when you talk about the fully developed thermally, so you talk about a region where the thermal boundary layers and the velocity boundary layers have met. So this is your region 3. Okay. So what could possibly happen if you apply a constant wall flux is that the wall temperature keeps rising gradually, and due to that, if you look at the property calculations in the case of external flows, all the properties that we calculated were based on T mean, which was T wall plus T infinity by 2. It is a linear average between the wall temperature and the free stream temperature. In the case of internal flows, we defined a T mean based on your mass weighted average for temperature U of r dr. So you have divided by integral U of r dr. So this is 0 to r naught, 0 to r naught. So you have to calculate the properties based on this mean temperature, and this temperature varies from the wall till the center line. Okay. And if you have a case where your wall temperature keeps varying, then therefore, and this will consequently result, if you look at the property calculation, the properties will be keep on changing due to the wall temperature variation. Whereas if you have a wall temperature which is constant, if you take this kind of an average, it will not vary the way that it varies for the case of q wall equal to constant. So this will result possibly due to this dependence of the thermal boundary layer on the Prandtl number. When these two merge, there will be a possible fluctuations in the thermal boundary layer. Okay. So it will not be exactly located and it will not be exactly merging at the center, but there will be some small fluctuations due to the property variation. Okay, because these boundary layer thickness are functions of Prandtl number, and locally the Prandtl number keeps changing due to different temperature values axially. So they attribute that these kind of disturbances in the thermal boundary layer will result in possibly a higher diffusion, heat diffusion in the case of constant heat flux, resulting in a higher Nusselt number. Okay. So this is about what, 16% higher than the constant wall temperature case. So one possible reason, this is a possible reason, although you cannot attribute it to a particular reason, this is one possible reason. What people say is that the variation in the properties due to varying much, the variation properties are much more in the constant wall flux boundary condition than the wall temperature case, and this will result in instabilities in the thermal boundary layer, which will possibly drive the heat transfer to be much higher than in the case of constant wall temperature. Okay. So this is one possible explanation, although in the textbooks it is not even mentioned, they just say generally that this is higher and they stop there, there is no concrete reason why this should be higher, but you should all remember that a constant heat flux case will generally result in a higher heat transfer coefficient than, so this is true even for external boundary layers, you have observed it. In external boundary layers the two boundary layers never merge, they keep the boundary layer keeps on growing, so there the fluctuations will be quite dominantly seen, whereas here the two boundary layers merged and therefore you can only attribute some fluctuations towards the center line, okay. So this is something that you have to pay attention. Now the next thing what we will do is we will move from region 3. So in region 3 we looked at constant wall temperature and constant heat flux separately, and we will now focus our attention to region 2, that is this region right here. So where you are hydrodynamically fully developed and the boundary layers still have not merged in terms of the thermal boundary layers have not merged, or you cannot say that your d theta by dx is equal to 0, okay. So you can only say du by dx is 0, the velocity profiles are fully developed but you cannot say the temperature profiles are fully developed. So for this particular region, it's a more interesting region, we will focus the rest of the classes, another 3 or 4 classes towards the region 2. So any questions on this so far? So I think I will give an assignment where you will be doing the shooting method, you can try out with an iterative guess, you can start with 1, 2, 3, 4 and you will find that progressively this will be satisfying. So once you reach close to the solution, you can take the guess values much closer, 4.1, 4.2, then you should see that it should converge. Okay, so we move on to the thermal entry length region, or the region 2, which I denoted, where you are hydrodynamically fully developed but thermally it is not developed yet. So for this case the first solutions were given by Graetz. So he did the first solutions for the region 2 as early as 1835, not 1835, it is 1883 and 1885, okay. So he produced the first solutions, in fact some of his papers are still available, but you have to go to a library and get it if you have the corresponding journal, but whatever Graetz did, he did it for only one case, for a very simplistic assumption that your velocity is completely uniform, that is a slug flow or plug flow case, okay. So later on people extended the Graetz flow solution to other generic cases where you can have a parabolic velocity distribution and you can have other boundary conditions such as constant wall flux and so on. In fact there is a person called Sellars, I have also uploaded a document on Moodle yesterday, so you can just have a look at it, where the Graetz solution was extended by this person, this group of people. Sellars is one of them, is the first author. So there is a document where they have proposed solutions to parabolic velocity profiles and also to cases where you have linear variation of wall temperature, wall flux is equal to constant. So there were further extensions of this first original Graetz solution. So this is popularly called as the Graetz problem also. And I will just list down what are the assumptions that he made. The first assumption that he made is that your radial velocity is 0 everywhere. The second assumption is the ratio of k by rho Cp into u is a constant. Now this is a big assumption, okay. When you say k by rho Cp, this is your alpha, So this you can understand that as a property could be constant, but when you say also u is a constant, so that means is assuming everywhere plug flow. Okay, so this is for a case where you have only plug flow, and therefore you can assume that this is your slug flow or a rod like flow, he calls it. Okay, he calls it as a rod like flow, so he assumes as it's like a solid rod which is passing through a circular tube. Okay, so where you have a velocity which is a constant and properties are also constant, and at the starting point where you are looking at the thermal boundary layer. Okay, so there the inlet temperature is a constant. So the region that you are looking at now is where your velocity boundary layers merged, and then you start the thermal problem. Okay, so suppose you start your thermal problem somewhere here. Okay, so strictly speaking you have to start it somewhere after the velocity boundary layers have merged. Okay, so from here you look at the thermal problem where the two thermal boundary layers grow and then merge. Okay, so this is completely your region 2. So now this is region 3. So you can now see that if you solve region 2 where you start from some initial temperature here, correct, from where the two boundary layers start growing thermally, already the velocity boundary layers have grown and they have merged, then you start the growth of the thermal boundary layers. At the inception of the growth of the thermal boundary layer, your temperature is equal to the inlet temperature. So from there they grow, so you are developing a solution for this region, thermally developing region, and asymptotically once the two boundary layers merge, you should asymptotically reach the solution that you had already developed for region 3, correct. So that is an asymptotic solution of the solution to the thermally developing region. So we will see that when we develop the final expression for asymptotic case, you will directly find that we will be reaching these two limiting values, okay, for region 3. Okay, therefore we could not, we strictly speaking we need not look at region 3 separately. We could have directly looked at region 2 and said that for the limiting case of x by d going to infinity, you directly reach your fully developed solution. Okay. So this is your assumption that at the inlet, everywhere inlet where you start the growth of the thermal boundary layer, your inlet temperature is uniform, it is constant, and so this is for the case if at x is equal to 0. So now your coordinate starts from a point where you start the thermal boundary layer growth. Okay, so this is your coordinate system. So it does not start from the inlet of the pipe, it starts from the point where your thermal boundary layer starts growing and where your fully developed velocity profiles are present. Okay, and T equal to T wall at R equal to R naught if your x is greater than 0. So he has looked at a constant wall temperature boundary condition. Okay, so at x greater than 0 the wall temperature is applied, less than that you do not have any thermal condition. Okay, and the other assumption he makes is that your thermal conductivity in the axial direction is 0, or you can say you neglect your axial conduction in comparison to the radial conduction. Okay, so then we can write down the energy equation for this case. So now so if you say the energy equation is u dt by dx is equal to, I am expanding, originally you have 1 by r, d by dr of r dt by dr, I can expand it, I can say alpha is common, so I can differentiate with respect to r keeping dt by dr constant, okay, so that will be 1 by r dt by dr plus I can differentiate dt by dr keeping r constant, so that will be d square t by dr square. So now this is your energy equation. So you are neglecting your axial conduction term with respect to radial conduction, you have neglected your radial velocities, your radial velocity is 0, so only your axial velocity is there. So these are all the assumptions based on the Graetz problem. So now you can assume a non-dimensional temperature theta like the way that you assumed before as T minus T wall. Now rather than using T mean, here I would like to use Ti. Okay, so why I am going to use here is that in your earlier case you somehow manipulated such that your dt by dx was a constant. Okay, so therefore you do not have to apply any boundary condition corresponding to x is equal to 0. In this case this is a partial differential equation. So for this you need a boundary condition for t at x equal to 0. So therefore at x equal to 0 your t equal to Ti. So to do that you can non-dimensionalize with respect to Ti such that at x equal to 0, so theta at x equal to 0 will be 1, okay, and theta at r equal to 1 will be 0, that will be T wall which is a constant. So you need two boundary conditions with respect to radial direction. So what is the other boundary condition? Should be finite, or d theta by dr should be 0. Okay, so substituting this we can rewrite this as, I can say my u equal to um which is a constant based on the plug flow assumption. So this can be written as um d theta by dx is equal to k by rho Cp, or I can just leave it as alpha here, d square theta by dr square plus 1 by r d theta by dr. So this is my non-dimensional temperature and these are the boundary conditions. So now in the case of thermally fully developed case, depending on whether it is a uniform wall flux or a uniform temperature, I can solve this directly, I can convert this into an ordinary differential equation and I could have solved it. But now in this case my theta is a function of both x and r, and I cannot put the condition that d theta by dx is equal to 0. So therefore this is a partial differential equation and I have to solve the PD as it is. So how do I solve the PD? I think most of you have done the solution of PDs before. What is the simplest technique to solve PDs? Separation of variables. Okay. So how many of you have done separation? Separation of variables. How many of you have done PD solution by separation of variables? So how about the other MTech students? I think at least in the heat transfer, advanced heat and mass transfer, it should be taught to you, I think. So I am not going to spend too much time explaining the separation of variables, but you should understand that you assume now this is a linear equation once you have your velocity. So any linear equation, now you can assume the solution for theta in this case, which is a function of x and r, you can split it into two solutions. You can assume that this is a product of two solutions, one which is only a function of x and the other which is only a function of r. This is the starting point of any problem for separation of variables. So then this is the assumed solution, you put it into the PDE. Let me call this PDE as number 1. So substitute the assumed solution into 1. What do you get? So this will be, when you differentiate with respect to x, r will be held constant. So this will be um r into dx by dx. On the right hand side you have, when you differentiate with respect to r, your x will become constant here. Okay, so you say x d square r by dr square plus 1 by r dr by dr. So now I divide both sides by x into r, capital X into r. So this will be by alpha, I bring it here, 1 by x, you have d. Now so this, since x is a function of only x, all this partial differentials will get converted into ordinary differentials. My x is a function of only x and capital R is a function of only r. So all these partial differentials here should be written in terms of the normal differential. So this will be dx by dx. On this side it will be 1 by r d square r by dr square plus 1 by small r dr by dr. So on this side I have everything as a function of x, on this side I have everything as a function of r. So on these two have to be equal. So this can be equal only if they are equal to a constant. So I assume that this constant is negative, minus lambda square. So why I put this is that if you look at the solution for x, then it will be an exponentially decaying function. If I put a positive constant there, it will be an exponentially increasing function. And what is this x standing for here? That is basically variation of theta with respect to x. Okay, so if you look at the variation of theta, you can see that as you start from this point, your t will be equal to ti. Okay, and that will be 1. So your theta will be 1. So if you plot your variation of theta with respect to x, so it starts from some value 1 and from there it has to increase or decrease. It has to decrease till it reaches the value of t wall, so where it becomes 0. So that has to happen exponentially, right? So this can be possible only if your constant is negative here. So this has to be an exponentially decaying function, only then your theta will behave in that way. Okay, so this lambda square, what I am using, these are called as eigenvalues. Okay, so this is the principal solution to the problem. These are called as eigenvalues. So therefore now I have two ordinary differential equations. So one is dx by dx plus alpha by I have lambda square x equal to 0. This I call as equation number 2, and d square r by dr square plus 1 by r dr by plus lambda square r equal to 0. So I can equate this separately to the constant, this separately to the constant. I have two equations, two ODEs. So ultimately what I have done, I have converted the partial differential equation into two ODEs. Now ODEs I can always solve them, I can at least use a simple numerical technique to solve the ODEs. Now what is the solution to the ODE number 2? It is an exponential solution. Okay, so it will be x of x should be some constant into e power minus lambda square by alpha lambda square by un. So this is my solution with respect to x. Okay, the other solution into x, sorry. Okay, the other solution is a solution to this ODE. So how do I solve this ODE? Now that is the question. Anybody can recognize what kind of an equation is this? I think in heat transfer I have taught. So this is called as a Bessel equation. So if for people who don't know what Bessel equations are, I will probably give a brief overview tomorrow about Bessel equation and the solution, general solution to the Bessel equation. Okay, generally for problems in cylindrical coordinate systems, okay, when you try to do a separation of variables, you end up converting that into a Bessel equation. And what are the boundary conditions to solve this? So how many boundary conditions you need for this? How many boundary conditions for this? For x, 1. This is a first order. Now this is a second order ODE. You need 2 boundary conditions for r. So what is the boundary condition for x? X at x is equal to 0 should be. Do we have any concrete boundary condition for x now? We don't have. We have only boundary condition for theta. So we know that theta at x is equal to 0 should be 1. So you can write this as x into r, x at x is equal to 0 into r should be 1, but from there we cannot deduce anything for x. So we will hold on and apply this boundary condition in the end. Okay. So now if you look at this problem, we can apply boundary conditions directly because they are homogeneous boundary conditions. Okay. So already we know that your theta equal to 1 at r equal to 1, theta equal to 0, and it should be finite at r equal to 0. So correspondingly, if you write theta as r into x, you can say that r at r equal to 1 should be 0, and your dr by dr at r equal to 0 should be 0, or your solution for r should be finite. Okay, so this is a ODE with 2 homogeneous boundary conditions, and this becomes what is called the eigenfunction problem. So how do you identify which direction is the eigenfunction problem? You identify the direction where you have 2 homogeneous boundary conditions, okay, and that gives you the direction where you find the eigenfunction problem. Why do you need the eigenfunction problem? Because you apply the boundary conditions, you find the roots of the eigenvalues. So that's why this equation is the eigenfunction equation. So once you know the eigenfunction, eigenvalues, then the r solution to r is the eigenfunction. Okay, so and then you can express your solution as a product of your eigenfunction into x. Okay, so this we will I'll explain, give you a brief introduction to Bessel functions, and then I will give you the solution, and then I will show you how to combine these 2 solutions. Okay, so any questions on this so far? So for people who have not had any course on partial differential, I suggest you try to learn up at least the separation of variables. It's a very fundamental thing. The rest of the classes will be working only with the separation of variables.